Hello everyone. This topic is Eulers' method. It's a way to numerically approximate solutions to differential equations. So this simple differential equation, which is separable, is actually an exception because the integral v to the x squared dx is what we call a non-elementary integral. So you couldn't integrate that by standard methods. So the idea is that we're going to approximate the solution to an initial value problem where dy dx is some function of maybe x and y, and we have that y is equal to x sub 0, y of x sub 0 is y sub 0, which is basically our initial conditions. So we're going to solve that numerically. The idea is first that we need a step size, or that we're going to call h, and we're going to start at x sub 0, y sub 0, and move n steps to reach our final approximation. So here's a figure that we'll draw, and draw it off to the side here, that shows the first few steps in the solution. So let's say we have x and y, and we have a graph here that this is going to represent our solution curve. So these are actually the values on this graph, or the solutions at the various x values. If we take an initial point, let's say x sub 0, y sub 0, and we shoot a tangent line off of that at that point, and we move h units. Okay, so the step size is going to be h. The idea is that we've reached a new point, x1 and y1. But then if we take that point and we imagine kind of tracing the solution curve here at this point, okay, and shooting a tangent line now that's with that solution curve to another point with a step size of h, we get a new point, x2, y2. And then you basically repeat the process. So now you get another tangent line, brings you to x3, y3, and so on. So when we take a single step and draw a larger picture here, let's say you get to a point x sub n, y sub n, and you want to know what's the next step look like. Well, it's going to be in the horizontal direction. It's going to be h units. Let me spread this out a little further even. So in the horizontal direction, we're going to say we've moved h units. And the slope of the tangent line, so let's say you had some curve in here, and this was the slope of the tangent line. And this slope is going to be the function evaluated at x sub n, y sub n. Because x sub n, y sub n is the point, and we have the initial value problem up here, we have that dy dx is equal to f of xy. So when we evaluate that at a point, we get the slope, because the slope in general is the derivative. So that represents the slope, and then we get to a new point here that we're going to call x sub n plus 1, y sub n plus 1. Create a right triangle out of this. And this point here is going to have the x coordinate of x sub n plus 1, but its y coordinate is just simply going to be y sub n, because it's the same y value of this point. Sorry, you didn't see me write the slope there. I didn't realize I got so excited. Okay, so then to get this side, it's just going to be whatever the slope was multiplied by h, because okay, so that's going to be h times f of x sub n y sub n. And the reason why that's true is because if you consider the slope as the change in y over the change in x, the slope is the f of x sub n y sub n. That would be change in y over change in x is h, okay? So, and then you could solve for the change in y, so you'd have h times f of x sub n y sub n to give us that change in y, or that vertical leg. Okay, so then that leads us to Euler's method. So the formula for solving an initial value problem with this initial condition is to the new y value that we're going to get, y sub n plus 1, will be this original y value. So finishing up kind of the derivation of the formula here, or at least the idea behind it, the new y sub n plus 1 is going to be the original y sub n, that's right here, and then plus this vertical distance, which is h times f of x sub n y sub n. Okay, so that's how the formula is generated. What each of these what happens with this situation is that the you get what's called a local error for a single step. So if you had some solution curve, so let's say that's the solution, and you have maybe this is your Cartesian system here, and you're at a point x sub n y sub n. If you take a step, so this is the value of x sub n. Let's say you take a step that's this big, so this is the difference here would be the h units. Then when you shoot a tangent line to get to this point, this is the new point, x sub n plus 1, y sub n plus 1. This difference, the vertical distance between the point that we have and with the actual solution curve, that's going to be what's referred to as your local error. But then when you take more than one step, those errors are going to accumulate. So for example, if this is the solution curve, I'll just kind of draw it roughly without labeling the points. Here's my first step. Shoot a tangent line now. Here's my second step. Shoot a tangent line. Here's my third step. So I'm getting further and further away from the actual solution curve. So that this now represents what we'll call the cumulative error. Where this is just what we were referring to the local error, just a single step. And again, this is our solution curve. Okay, so that's the idea. And this is an iterative formula, as we're going to see now, and we'll come back to it. So our example. First off, what I did on the exam was every question is going to be frozen up here. Okay, there we go. Every question is going to have you find the exact solution by a method that we've already studied, and then use the approximation method to approximate and make a comparison between the two. So in this example, we're told that we're given this initial value problem and the exact solution. And we want to verify the solution by separation of variables and then apply Euler's method. So first off, verification by separation of variables. So we have y prime, which I'm going to call dy dx. So we'll start with y prime equals 3x squared y, and then we'll call it dy dx for the sake of separating the variables. Then we'll separate the variables. We get dy over y equals 3x squared dx. And integrating, get the natural log of y, x cubed plus c. And so now Eulerizing, remember e to the natural log of y is y, equaling e to the x cubed. I guess I should have called this the natural log of c, right? We had done that in the past. And this is that, what I refer to as Eulerizing, right? E to both sides. And then this e to the x cubed plus natural log of c, we could bring the c out in front. That's going to be c e to the x cubed. So recall doing that from unit test 1. And then the initial conditions. So the initial conditions were that y of 0 was 3. So then that gives us 3 equaling c. So then our solution, y equals 3 e to the x cubed, and it's verified. Okay, so you can see we get the solution 3 e to the x cubed. Okay, so now we want the new stuff, Euler's method. Okay, so his method, I'll write the formula here. Y sub n plus 1 is equal to y sub n plus h times f of xy. And we have the initial condition that y of 0, again, is 3. And our function f of xy is the 3x squared y. That's the y prime, or the dy dx. And again, the initial condition, y of 0 is 3. Okay, this says to do it twice. The first time with the step size of h, equaling 0.25, over the interval, I'm going to underline that twice, over the interval from 0 to 0.5. So we're just going to have to take 2 steps to get to 0.5. The first step, we're starting at x sub 0, which is 0, and x sub 1 is going to be 0.25. So that's going to be our first step. So y sub 1 is going to be the initial y value of 3 plus h, which is 0.25, times the function. And I always like to put the function in brackets. So times, and then going to put it in brackets just to make it stand out a little bit. And it's 3x squared y, where x is the original x sub n value of 0, so 3 0 squared, and then times y, which was 3. And it turns out that that extra term there just all goes to 0, and we just get 3. So now the second step brings us to the endpoint of x equaling 0.50. And so y sub 2 is going to be the previous y value, which was still 3, but then plus the h times, now we have 3 times the previous x value, which is 0.25, that needs to be squared, and then times again that previous y value, which is 3. And obviously you're going to have to use a calculator for this, so we get 3.140,625. Okay, so that's the first set. Now let's do it for h equaling 0.10. So now we're going to need 5 steps to get there. In the first step, it's going to be where we take a step to get to x1, which is 0.10, or just 0.1. And y sub 1 then is going to be the initial y sub 0, which is 3, plus the h, 0.25, times the function. 3 times the initial x value, which was 0, squared, times y, the initial y value, which was 3. So that again just gives us 3. So then we go to x2, which is 0.2, and we calculate y sub 2. And y sub 2 will be the previous y value, 3, plus the step size, 0.25 again, times, now the function again is 3x squared y, and so we have 3, the previous x value, see, because that's what we're doing, is we're going off of the previous, I should have wrote here, f x sub n, y sub n. So this is f of x sub n, y sub n. See, it's the previous x value to get the new y value. So the previous x value was 0.1 in this case. That has to be squared, and then the previous y value was this 3. Okay, and then if you crunch all that down, you get 3.009. Okay, next step, x sub 3. So 0.3, y sub 3. Okay, now you need the previous y value, right? Because in the formula it says y sub n. We're getting y sub n plus 1, so now we're up at 3, so we need the second y value, previous y value. Now the 3.009 plus the 0.25 times, and then the function 3x squared y, but the previous x value was 0.2. So 3 times 0.2 squared times the y, previous y value, 3.009. Okay, and if you crunch that down, you get 3.04518. 108, excuse me, what I came up with. Okay, we got 2 more steps to go. So x sub 4, 0.4, fourth y value, previous y, 3.04518, plus step size, 0.25, times the function. And the function again is 3x squared y, so it's 3x is the previous x value, 0.3 now, which is squared, times the previous y, that's 3.04518. And that gives us y4 to be 3.1 127, 325, 916. I'm just bringing it out to as many decimal points as the calculator displays. Okay, finally, the fifth and final step, y sub 5, previous y value, that's the 3.127325,916, plus the step size 0.25 times the function. And again, the function is 3x squared y, 3x previous x value 0.4 squared times previous y value, 3.127325,916. Alright, and then finally crunching all that down, get y sub 5 is 3.27743756 is what I got. Okay, and then the directions ask us to construct a table showing 6 decimal place values of the approximate and actual solution. So when we use the actual solution, let's set up the table first, and then I'll show you what we mean. Let's say this is our x value. This will be the step size using h is 0.25. This will be the step size using h is 0.1. And then here will be the actual values. And let's see, I'll label the x's. We'll do 0.2, 0.1, 0.2. We're going to have to do 0.25, 0.3, 0.4, and then 0.5. Okay, for h equaling 0.25, the first was just 3. So that's way up here. And the second one at 0.5 was 3.140625. These other ones didn't exist. So 3.140625. Okay, and then all the values of h equaling 0.1. So those are the results, the 3, 3.009, 3.045, 108, and then these values. So let's list them here. 3, 3.009. We didn't have one for 0.25. So then 3.045, 108 to 6 decimal places. 3.127,326. And 3.277,438, rounding. Okay, and to get the actual value, we have to use the solution that y of x is 3e to the x cubed. Okay, so that was our actual solution that we had proven by separation of variables, recall. 3e to the x cubed was the verification, and there's the formula there, or there's a solution there. So, for example, when x equals 0.1, you've got y of 0.1 to be equal to 3e to the 0.1 cubed. And then obviously you're going to use a calculator on that. And that comes out to 3.003002. So that was the actual. The approximate was just 3, so we're a little bit off. Continuing, if you do x equals 0.2, same concept. Just plug in a 0.2 into the actual solution. I won't show any more of those. I'll just show the results. Get 3.024096. 3.047243. 3 point, and obviously you can check me, 0.82 and you can tell how we're getting further and further away. That's the idea of the cumulative error taking effect here, but still not horrible approximations. Good to the nearest tenth at least, I guess, for the most part, as we get further away, and again, bigger error. That's because those little steps are accumulating. Alright, so finally 3.399445. Okay, so we're a little bit off. Not as bad as the step size of 0.25 though. 0.1 is a little bit better. But taking so many steps is what's causing that to veer off. Okay, so that's the method, and we'll come back and do the improved Euler method. So we're going to see by the end of this, we got 2 more methods to go, and by the third method, we're going to have an approximation that really gives accuracy with minimum step sizes.